Hello, today I'd like to talk about triangle rasterization. These are the today class objectives. I hope that you can understand the triangle rasterization during using edge equations. Also, we'll talk about various techniques for parameter interpolations. And then also, I hope that you can realize the benefit of the incremental algorithms. Also, last time we talked about the various techniques of the clipping and culling methods. Also, some of them used these edge equations. Before we talk about the rasterization, so far we talked about the different types of the transformations. Initially, suppose we define a model in the modeling space, then we transform into the world space, and then we perform the viewing space, and then we actually turn the coordinate defined the world space into the something in the I space. And then also we talked about this projection, the matrix. By applying this project matrix, we actually change the coordinate of in the viewing space into the cliff space. We didn't really define this cliff space, but actually that's the space where we apply this projection space. Then if we divide then we perform this divided by the W, which is actually the homogeneous coordinate. Then we are actually getting this NDC coordinate. And then we perform the viewport transformation. Probably we talked about almost the beginning of this computer graphics course. Then we will actually compute in some of this color or the index in each this window pixel space, basically the screen space. Okay, so basically once we perform, basically once we actually perform the series of this transportation, then somehow we convert this vertex representation defined in the world space to the pixel representation. Then suppose that we actually compute the coordinate of those vertices in this kind of this pixel space. Then the next question is that given the pixel, we need to decide whether these pixels are within this triangle or not. For example, for this pixel, actually these pixels are within this triangle, right? Then we know this is covered by this triangle. Then the next question is that we need to compute what the color within the pixel. So basically, this is actually in summary this coverage determination compared to which pixels belongs to the primitive within this triangle. Then you need to compute the parameter. In this case, actually the basically RGB color. For example, we need to find RGB color value for each vertex, right? Then within this triangle, we need to actually parameterize those colors. So we need to compute the parameters at covered pixel from the parameter associated with these primitive vertices, the triangle vertices. That's the two problems that we need to address within this rasterization process. Typically, further this coverage determination, we perform typically the coverage problem is actually the 2D sampling problem. For example, for this pixel, actually this 2D area, right? And then we need to actually to this one of the actually one direction might be to compute this covering area under this triangle area, right? That we computed this some sort of irregular shape that overlap between this rectangular shape of pixel triangle. But that's too difficult to computing exactly overlapping the region. It might be polygonal shapes. So instead of addressing this very complicated 2D sampling problem, we actually commonly reduce down into the 1D problem of just checking a sample point. Instead of computing this overlapping the area, we just checking only the center of pixel. If the center of pixel are within the triangle, then we know that it will be we can decide that it will be within the triangle. Then that's actually the example of converting this complex 2D problem into the 1D problem. There might be other ones. I mean, basically we can compute the distance of primitive to the sample point and other ones, but they're checking whether the sample point is the inside of the primitive. That's actually the most common approach. So our discussion, there are a lot of cases, actual implementations of the restoration process was actually implemented in the hardware, GPU hardware, maybe based on this a simple process. So Now I will talk about the more detailed rasterization process, but there are many different ways of performing the rasterization, but there a lot of actually the cases there's a lot of the techniques, but one of the most fast techniques, this technique that we'll talk about, the rasterization process with edge equations. So given these vertices, we first compute edge equations from vertices, then we compute the interpolation, this kind of the interpolation equation from the vertex parameter, and then we traverse pixel and evaluating these edge equations. And then some of the vertex are within the theory of this edge equation, then with actually the compute the color, we compute the color of that triangle and assign the color to the pixel. Basically, in other words, that's interpolating this parameter at those vertices. I will talk about details of this technique later on. So basically, the restoration process based on this edge equation. So then we need to compute how we can set up this edge equation. Basically, suppose that you have two vertices v0, v1. Then we can compute this edge equation coefficients. In this case, the a10, b10. Here, actually 10 actually indicating that this edge equation coefficients coming from the vertex 0 and 1. Then we just start to do that. We just compute the cross product between these two vertices, and then we actually we get this one, and then we just assign this a10, b10, and c10. Then edge equation says nothing but something like this. And then the pixels are at that particular location x and y. With the treated edge inside, if we plug that value within this edge equation and it gives a positive, then we treat that is inside. Then the question is why we actually applying this approach. So here, let me give you the intuitive explanation. So basically, suppose this actually we have the 2D v0, right? But if you're actually using this kind of homogeneous coordinate x0, y0, 1, then then basically you can think that this v0, then we can actually think about it. What are the actually corresponding homogeneous coordinate that are mapping to this v0 in the 2D space, right? Here we just using the x0, y0 to 1, but obviously we can use the arbitrary homogeneous coordinate, the w, right? That it means that this 2D value mapping to a line in the 3D space, including homogeneous space, and this another line. Then basically this line in the 3D space that passing through these two vertices mapping to the plane in that 3D space. Then you'll know that the line passing through v0, this plane that passing through v0, v1, also they're passing through the origin in that 0, 0, 0, in the 3D space, right? Then you can actually visualizing the plane that actually passing through the origin. Then basically how can you compute the normal of that plane in that 3D space? Then obviously we actually computing this kind of the vector. Basically by performing these two vector from the origin to the v0, another vector from the origin to the v1. Then we actually these are the cross products, and then we can actually define the plane that passing through this origin by like this. Then we can actually have this one. It basically I just talk about this kind of geometry interpretation with the text, but I recommend you to actually draw the line and then and think about it. Then you can get the main idea. If it is unclear, I recommend you to check out my book. Then there's actually questions, the issues. Suppose that actually we actually decide whether the triangle within the triangle or not by actually checking the certain center of the pixel, right? But in this case, actually there are two triangles, triangle 1, the red one, another triangle 2 with the blue one. But somehow the boundary of triangles are passing through exactly the center of center pixels. Then if we actually plug in those region, it will be the 0, right? Then we need to actually but basically we need a way of consistently assigning this pixel either one of the triangle. If we just allow these triangles actually at that case, it's basically education turn out to be 0. We just then if we give if we just treat that this inside either any of this triangle, then pixel color becomes dependent on the order of the triangle rendering, right? If we actually render triangle 1, triangle 2, the final pixel will get a blue. If we render this triangle, triangles into triangle 2, triangle 1, then the pixel will get the red value. Obviously, we don't want that. Also, it creates a problem when rendering transparent object, double hitting. I mean, basically basically there are two triangles actually assigned to this pixel, and then probably the transparency comes with some sort of the opaque value. 그러니까 투명도가 있건 opaque value, the 투명도. Then obviously if we render the restaurant two triangles together, then opaque value keep going on, and the appearance obviously looks different. Also, if we do not render any of them, then obviously there will be whole. Obviously, these are not a good solution. Better solution is that's why we need the tiebreaker. We need to assign either one of them in a constant way to that pixel. Common tiebreaker actually looks like this. So given these two triangles, so basically here we just look at the normal of each educations. Basically in this case, given this tiebreaker, we just decided that the normal of each education set towards that direction, that direction, we actually we choose that triangle as we let that triangles assign have the color within the pixel. So basically, this is actually the one. We first look at the x direction of the normal vector. If the a value is positive, so it means that the normal vector should be heading. Look at that direction. Then if this is turned out to be the 0, then we look at the y component of this normal. Then also the y component should be this positive value along that direction. So then if we're using this one for this triangle, we'll get this positive value, and then then this pixel will get the blue value. So in summary, the coverage determination becomes like this. If you plug in the center of the pixel xy within the education, that should be that is the positive, or if turned out to be the equal, then we'll look at this Boolean value of this one. This should be the positive, then it's pixel covered within that pixel. Of course, we will have this kind of shared vertices cases. Also, we can also use using this inclusion direction. For example, we just choosing this certain region that having the certain triangle that having that direction. We can actually using that approach. Or another approach is actually we can snap vertices to the subpixel grid. So even though basically so in this case, actually, this actual center pixel, but we somehow we don't allow any arbitrary coordinates. So, for example, we actually somehow quantize this region into some of the sub regions, and then snap vertices in a way. Also, we give a little bit of this offset. Then we actually design in a way that coordinate cannot be exactly on the center. Then basically no vertex can be at the center pixel, so it means that we actually avoiding that kind of shared vertices. Also, this is actually quite this actual blue one is actually snap vertices, but it's quite possible since actually we don't use this actually the very accurate floating operations, plotting representation for these vertices xyz coordinate. Instead, we can actually we wanted to use the very compact or the very memory efficient way of processing this one. We typically actually quantize this floating variable into the small bit, like the 20 bit, something like that. Then obviously this is also quite a doable approach. So now actually we decide that whether that certain regions are actually within this triangle or not. Then the next question is that what are the color? So that's the actual interpolation problem of the parameter. Parameter could be many other things. It could be the RGB value, even normal value, or texture parameter, and so on. So in this case, we need to specify the parameter, say the redness R value at each vertex of the triangle. Basically, each pixel of this within this image space, and then we can actually using this kind of applying the linear interpolation. So we just treat that here actually we look at this actually x and y space, this image space, and then we look at this redness is the value here. In this case, there are certain redness value over there, very big redness value. At that vertex, we have small redness value, and then we just treat that there are some sort of the linear plane passing through that red value at each vertex. So in other words, the redness value r of x and y have this kind of linear equation, and then given the x and the x and y, we have this ar, br, cr, this the coordinate. Then there are three unknown AR, BR, CR, but also there are three vertices. Actually, we can set up the following linear equation. So, for example, given this first value R0, then by plugging into the x and y0 into that kind of linear equation, then we have this R0, right? Then you plug in AR x0, BR y0, and plus the CR. That's the actually linear equation that we set up before. With the same thing with another vertex, the vertex 1, vertex 2, we can actually have the three different equations. Here I'm showing the matrix representation. Then these R0, R1, R2 are the known value. These are also we already know the coordinate, right? The unknown is actually the coefficient of this redness planes of this coefficient AR, BR, CR. And then to compute this one, we need to actually invert this one, invert of the 3x3 matrix. Then this AR, BR, CL actually they have this value. Then we take the inverse and then applying there, then we will get this equation. In summary, AR, BR, CL, R0, R1, R2. This actually inverse of this one. I mean, in my age, I almost forgot that this inversion or inversion equation of the matrix. I hope that you can remember this one. If it's unclear, I recommend you to check it out wiki, also to discuss with the ChatGPT. There are certain equations here also divided by this determinant. But actually, here let me briefly talk about this triangle area. So if we actually there are many different way of the measuring the triangle area, but actually one of equation like this, the half of this determinant of this one, then we got this equation. But surprisingly, actually here actually these terms actually coming from the edge equation. Actually edge equation. For example, here I said that this is actually give the notation C0, C1, C2, but C2 actually here I think C2 is actually basically in the earlier of our slide we actually set up this edge equation, right? We define A01, B01, C01. Here C2 actually this is actually coefficient from between vertices of the 0 and 1. And if the area is 0, it means that the triangle is not visible. And negative area case, actually this triangle is actually back-facing. At that case, we know that actually this back-facing, so we can actually reject this triangle, drawing this triangle if we want to use the back-face calling. Otherwise, if we want to rasterize this one, we actually flip these edge equations, and by multiplying the -1, then we can actually make it the front face, and then we can also rasterize this one. Also, then we can actually rewrite the prior the matrix equation that computing AR, BR, CL. Basically, I can actually go back to in this actual PowerPoint presentation. So I recommend you can actually go back to the PDF file of the lecture file, and you can see the together here. The primary equation that I talked about before actually can be basically reformulated, looks like this. Here actually we actually had a very complicated determinant, but it actually turned out to be the area, triangle area, R0, R1, R2, and also there are many these complicated terms, but actually it turns out that they are actually coming from these edge equation coefficients. Basically here actually E0, E1, E2 are the vectors of the edge equations, and then E2 actually is nothing but the education coefficient A01, B01, C01, they are coming from the edges coming from these two vertices B0, B1. So basically here, if you want to know the more clearer notations, actually I didn't really define E0, E1, but I recommend you to look at my book. So basically, the main message is that once you set up the edge equation, those components are already given by the coefficient edge equation. We can compute also the triangle area with the edge equation. Then we can very efficiently compute actually set up the coefficient of the linear plane of that one. Then we can perform the parameter. We can also we can very efficiently perform the color interpolations or the many other parameter parameter interpolations. So you can see that actually a lot of the rasterization process with educations are very highly optimized actually. Also there now actually there we can actually given the scene with the many triangles, also there are many these different objects, right? And then we can actually rasterize, right? But we actually make sure that only the visible triangles actually within the screen. So for example, basically these the kinds of the dark green, the box actually occluded by this cone, right? So when you actually rasterize some of the dark green triangle here, we make sure that actually dark blue triangle behind this cone should not be visible, right? So when rendering multiple triangles, we need to determine which triangle is actually visible or not. So now here we actually use G value. Also we actually store the depth value G value into the G buffer. This actually, in addition to the RGB, also we have the depth buffer G buffer to resolve this kind of visibility. So we actually store depth value at each pixel. Initially, we initialize the G buffer with the this one in the, and this basically here one if we actually look at this perspective G value, actually they are actually lying in between 0 and 1. 1 is indicating far value. So initially we actually assigned everything is actually located very far away. And then we also perform the linear interpolation of this G value across this triangle. And then we compare that G value with the already stored in the G value at that pixel location. And then obviously initially that G value actually have this very big value, right? And every triangle that we rasterize initially will have smaller value than this one, and then we write that depth value. We actually override it. We override that value into the G buffer. Also, we actually we also write that the color at the RGB channel, right? And then we keep doing that, and then suppose that we actually render this one first, and then if we actually rasterize this one, then that portion, then at that case, the G value of this blue triangle located more far away from more bigger value than the stored in the G value, right? Then we don't allow them to actually we don't allow them to actually override the depth vector of RGB buffer. That way, actually, we can have we can render this kind of visible, only visible the triangles. This technique known as the G buffering, very simple technique, but also I didn't really talk about the many other alternatives. It turns out that it's the most naive approach, but actually it works very well with the parallel computations. And that's why actually in the end this technique adopted in the recent GPU-based rasterizations. Okay, so given this, also we can given these vertices, there are many different ways of traversing pixel. We can traverse this pixel in that way, and then we check whether it's within the triangle or not. But typically, we also wanted to accelerate. So typically, we actually restrict the traversal into the primitive bounding box. In other words, we actually we actually apply in this case, actually, we have a certain this tile representation, and then some of the tile actually totally outside of this triangle. We don't traverse, and then also this tile totally within this triangle. Then we actually set the color within there. For other one, we actually traverse there, and then we actually check whether it's inside or not. So also in other words, there are many advanced techniques to accelerate this process. Think about it. There are so many triangles, so many pixels, and definitely we actually need a very efficient way of traversing this pixel and rasterizing, computing color of this triangle. That's why actually there are many optimized techniques. Also we can think about it other more this faster technique. One of the example method is incremental techniques. So some computation can be saved by updating edge also the interpolation equation in an incremental way. suppose that actually at a location x and y, you actually the evaluate the this education, right? And then next pixel here actually the basically the given the under just the let me use this pen. So this actually the x and y location, and the next pixel, this one actually, this is actually this is the x and y. This actually this location is the x plus the delta here, just the next pixel, right? And then for the next pixel, we can actually plug in this x plus delta, it's this equation like this, and then this is nothing but given this the prior the actual equation that we evaluate x and y plus with a delta, right? Then we can actually by adding by multiplying this one and then adding this one, we can actually update this to education. We can do the similar approach for the y direction. So in other words, education can be updated with a single upfield this operation, and then we can also we can gather this a little bit of the saving here and there. So in summary, so basically this is known as triangle setup. Given this, once you compute the vertices in the image space, then you compute the edge equation by performing the cross product, and then you can also compute the triangle area with a few additions. Then you call zero area of backface triangle, or the flip the edge equation, and then you also compute the interpolation equation. Basically, this is just a few matrix vector product with per parameter. So basically, everything can be actually very efficiently carried out. But when you actually render a lot of the massive data, for example, actually this actually the model, the same Matthew model consists of the 400 million triangles, and then suppose that you just had this 1,000 by 1,000 image space, which means that 1 million pixel, and then if you have to render this kind of the big model, in this case, I suppose I have the 100 million triangles, then it indicates that there per pixel on average per pixel about 100 visible we actually about 100 triangles actually the mapping to that the pixel. Obviously we cannot see that the details of the 100 triangles through the only one pixel, right? Then obviously it takes a lot of the cost to even to rasterize this every single triangle. We need to specify the 3 vertices, edge equation, blah blah blah, right? So we definitely need actually the better way of handling this kind of massive model. One of the well-known techniques is the multi-resolution, or the levels of the detail technique, LOD techniques. Its main idea is to render with the fewer triangles when model is farther from the viewer, this viewer. And then basically this bunny model consists of some triangle. Then if this model actually they're located very far away here, then obviously this bunny actually mapping to the more smaller region in the image space. Then it means that we cannot see the detail here. Then we can actually we can even use the lower triangle. It means that we actually using the lower resolution, and then we can actually render more fastly this triangle if the model actually located far away. That's the idea of the LOD, or the polygonal simplification. In other words, we simplify this triangle from here to there. This is the typical operations of the polygonal simplification, the method for reducing the polygonal count of the mesh. Here, basically to reduce down these triangles, here actually we perform edge collapse. In this case, two vertex VA, V2. We collapse this edge by making the VC, and then you can see that by doing so, these two triangles actually they're reduced, right? Then by performing every edge collapse, we can reduce down to triangle. We can actually iteratively perform this operation, so that we can have this kind of this reduce. We can actually represent this bunny with the pure number of the triangles. Obviously, there are other issues, right? When you're performing this operation, we need to maintain shapes. But if you're interested, you can actually take it out. You can check out more details. But here, I'm just giving high-level idea. And then, given this dragon model with the 50,000 model, we actually computed this kind of reduced simplified model with a small number of triangles, another triangle. Then, if you just using this one, the model looks very crude, very coarse. So then, we actually we pre-compute this kind of discretely simplified meshes, and switch between them at runtime. In other words, if the model is very close to the viewer, we're using this one. If the model is far away, then we use this one. Located more far away, then we can use this one. Obviously, there are not much difference when you are using this one when the model is located very far away. Then we can just using this the 2000 triangle. So then, obviously, instead of the rasterizing this 50,000 by rasterizing the 2000 model, we can actually accelerate a lot of performance. That's actually the kind of the using the static LOD. We actually computed this kind of the different set of models. Then basically the when you actually render this model, and then at some point we have to use this model. Then there are a little bit of the visual artifact that's known like the popping artifact. You might notice that when you actually play some game with the many triangle. That's why. So a lot of the game engine or game we're using this kind of static LOD techniques. Also, there are many advanced techniques. This is actually this is paper about 2007 from the Pixar. You've probably seen that in some movie, in the Pixar movie or some other one, there are many little leaps and the object, right? And then even though you simplify each individual the triangle, that's not enough. And then there are so many different objects, the leaps, right? And then this approach is that applying this kind of some sort of the simplification of the aggregate details. I mean, basically instead of drawing the many the leaps, they just they randomly randomly call out some of the leaps, and then they actually accelerate the rasterization process. That's they call it stochastic simplification. Also, there are the paper they presented last year, at the 2023. That's the deep appearance pre-filtering. So here, this is actually the simplification technique, but they're using the deep learning for the ray tracing technique. So this kind of technique now they're designed from the rasterization even to this ray tracing. Okay, that's it. So by now, I hope that you can understand the triangle rasterization process using the edge equation, which is very important. And also, I talked about different technique for the primary interpolation. I hope that you can actually you can see the benefit of the incremental algorithm. These are the regular homework. Go over the next lecture slide. Watch some of the paper video from top tier conference related to the computer graphics, and submit your summary paper every Monday class. And then try to submit question paper 2 times during the whole semester. Basically, I try to encourage you to come up with think about it, this lecture material. If there's some of the questions that naturally rising to you, just actually share the question with us. That's it. Next time we'll talk about illumination, then we'll talk about some of the this texture mapping technique. That's it. Thank you. Bye.